Sukai is going to tell us about chasing progress, not perfection. You can use this for back and forth if you like.
Oh, I think I can just use this one. Okay. Good morning. My name is Sukai Huang, and I'm glad to be here to present this work, revisiting strategies for end-to-end plan generation. So this work is motivated by the critical debate within this planning research community. The debate is, can LLM genuinely learn to plan, right? So I would like to give you a big picture of the work before we go into details. In this work, we reassess the effectiveness of different LLM fine-tuning strategies that have proven effective in enhancing LLM's reasoning capabilities in other domains like math problem solving, code generation, and we want to test them in end-to-end plan generation tasks. So the strategies include permutation, chain of thought into different styles, self-correction, and also reinforcement learning. The result is mixed. And we see within the planning community, works like PlanGPT and Plansformer have made the claim that LLMs can learn to generate valid symbolic plans effectively by fine-tuning, not mentioning the works outside of the planning community. For example, I think some works try to use LLMs to solve Minecraft, right? They also consider that as kind of planning. But for those who are unfamiliar with fine-tuning, it refers to updating LLM's parameters through supervised learning on a data set structured as text sequence. The goal is to train the model to predict the sequence tokens by token. Okay. And we also have this criticism within the planning community. So I think the Rouse team, they try to argue that LLMs struggle to find valid plans when the problem become more complex. So they have this example by increasing the complexity of the problem by increasing the plan length, and they find out that LLM is not able to generalize when the plan length gets larger. Okay. Therefore, our work wants to further contribute to the debate. Reassessment is needed. First of all, we believe that results from fine-tuning LLMs for planning tasks have been overly optimistic. Secondly, we want to go beyond simple yes or no answers about whether LLMs can generate a valid plan. We want to provide a softer metric such as executability to evaluate the quality of the generated plan in a more granular way. So executability means the precondition of the action generated by the LLM is fulfilled whether or not. So that's the executability. And lastly, we see a group of strategies that have been successful in other domains, like math solving to enhance LLM's reasoning abilities. We are interested in knowing whether these strategies can also be applied to planning tasks. And to clarify, our work focus exclusively on the end-to-end plan generation paradigm using LLMs. So there's no external MCTS, no LLMs modular pipeline or other external things. So it's just LLM standalone. Okay. about the data set, to prevent the concerns of data contamination, that means the model has already seen the test instances during training, we extend the plain bench dataset introduced by Velmican et al. And compare to other works, we made the following two significant changes. The first one is to reduce the size of training set. Previous works like Plansformer use approximately 14,000 training instances per domain to fine-tune their LLMs. However, we observe that with such extensive training set, models tend to memorize the entire problem space. Consequently, test instances often differ only in superficial aspects, such as object renaming, and this scenario lead to overly optimistic performance claims. And secondly, to further ensure that the model is not memorizing patterns but plan from their first principles, we introduce test problem with longer plan lengths. So this ensures that the solution of any training instances can only at most be a subsequence of the solution of the test instance, ensuring that the model cannot simply reuse memorized patterns. So now I will introduce the strategies we have explored. The first one is permutation. It randomly rearranges sentences in the query and thus create a diverse set of planning questions that have the same semantics. So if you look at the example here, this strategy is simple. We just rearrange the order of the sequences, but the semantic keep remained. And okay. The rationale is that it encourages the model to learn the underlying semantics rather than overfitting to superficial word patterns. Okay. And the chain of thought. Due to time limit, we do not go into the detail about chain of thought because this is quite popular. And the essence of COT is to add intermediate reasoning steps before directly predicting the final output. So in our training data, we further add goal distance estimation and the precondition and effects of grounded actions at each planning step directly in the training dataset. So when we fine-tune the LLM, they need to predict those information as well. So the rationale is to encourage the model to consider the mutual relationship between them. Okay. Self-correction is another popular technique. Under this method, the training data is augmented to have synthesized mistakes and the correction to these mistakes. This can be seen as a form of contrastive learning and expected to avoid the model from exposure bias. So if you look at the right-hand side, this is the example. We deliberately add errors, and we have a wrong tag to show this is the error, and try to let the LLM to fix it. Yeah. Reinforcement learning is another popular fine-tuning strategies for LLMs when the task is related to sequential reasoning. And I think this technique is quite popular at the beginning of this year due to DeepSeek R1, right? And however, a binary valid or invalid plan reward is really sparse. So in order to provide a smooth gradient for training, this is how we design the reward signal. If val finds the generator plan to be valid, the reward is 1. But if it's not valid, instead of having no rewards, we propose using longest contiguous common subsequence to be partial rewards, so that we provide a smoother gradient for the model to learn from. And note that this is just one of the many ways to design the reward signal, and it's still an open question on how to design a better reward signal for training LLMs. Okay. And we have gathered some important insights from our work. First, we found that the previous statement that LLMs can learn to plan effectively through fine-tuning is overly optimistic. We found that the vanilla fine-tuning process does not guarantee the model to generate valid plans for out-of-distribution test instances. And our second key finding revealed that the strategies previously deemed ineffective actually yield incremental improvements in the executability of generated action sequences. This discovery suggests a more nuanced direction for future research, focusing on how to maintain the executability while simultaneously improving the model's search capabilities to reach the desired goal. However, we also found that self-correction, while effective in recognizing mistakes and improving the executability of the generated plan, did not significantly improve the model's ability to reach the goal. And finally, reinforcement learning consistently help improving both the validity and executability of the generated plan in out-of-distribution test data. And this finding aligns with other recent work. For example, DeepSeek R1 is no more recent, actually, but yeah. Okay. I want to talk about future direction. And a core question keeps popping up. Is the next token prediction paradigm, the foundation of today's LLM's work, fundamentally flawed for planning? So there are a lot of debates on this right now. So we got some critics. I think there's a paper from ACL found that they argue that next token prediction is just cannot do reasoning, but there's still people saying that the next token prediction is not fundamentally limited, but the training process can cause the model to overfit. So yeah, that's still an open question. Okay. Thank you.
Thank you. There are questions.
Yeah, I was looking at your reinforcement training loop for Audi distribution. I am accordant with you that reinforcement learning is the key to assess new capabilities, but if you want to test OD, you cannot have the plan. If you can go back to the slide, and you use a reference plan in the reward function, you are pretty much using a EED distribution over the reference plan. So you are not going OD, you are changing your loss function. Can you comment about this?
For these reinforcement learning signals, yeah, so we actually have this situation that RL is not able to just further fine-tune within the training dataset, because once you fine-tune the LM in the training dataset, it's just have the full rewards, because we have already tested in the in-distribution data, LLM plan can just reach about 100% validity. So if we still continue to add RL on it, it's just there's no gradient there because it's already saturated. Yeah, so we still need the kind of validation set to do the RL. Yeah.
Any other questions?
Thank you for the presentation. Just an observation. At the beginning, you mentioned Transformer and Plan GPT under the categories of fine-tuning. That actually Plan GPT does not fine-tuning. It trains from scratch, completely from scratch, a transformer. And the other observation is that you said at one point that with 14,000 plans, you basically have all the plans in the domain. That's not true. Depends on how many objects you have in the domain. So if you, for example, have 200 blocks in the blocks world, 14,000 problems is far from covering all the possible problems that you have.
Yes, you're right. The thing here is that in most cases, researchers, when they evaluate, they try to also limit the length of the plan. So they try to constrain the problem space. So even if you have a very large number of objects, but at the same time you constrain the plan to be limited, then only a partial objects is used during the planning process. Yeah, that's the issue here.
Thank you, Sukai. Can you go to the reinforcement learning one? Just, I want to check if I understood. So for the reference plan, you got it from a symbolic planner, right?
Yes.
So, but how do you know there may be many reference plans, and the one that generated plan may be pretty good or compared with another one? So do you get many reference plans and you check the best?
Yes. I actually we and Nia considered this before. So one of the future work is that we can have a collection of reference plan and to do some aggregation on that.
Right, and you said you also there are many other ways of getting the reward.
Yes.
Yeah.
So
How good is this one? I mean, I was thinking, first thing I was thinking is measures like the using BPM and misalignment, number of changes, could be more, a little bit more informative that this.
Yeah, true. The idea behind this one is to get the alignment between the reference plan and also the current plan. So that's basically some kind of measuring the distance, how far you reach the actual value plan. And yes, there's a lot of different way to design rewards. For example, I remember someone suggests that we can use some kind of coverage-based rewards so as to encourage the LLM to explore the space. Yeah.
For the presentation. So you said that you have this intuition that next token prediction may not be the best way. I wanted to ask, what is your alternatives that you would like to test? And to me, it seems that because planning is sequential decision making and you find an action and then you want to find the next one, it seems that next token prediction could actually be a fit. But I wanted to ask about your opinion. What is the other option that you would like to test?
Okay, so I think currently most LLMs use next token prediction, and as long as we have high quality training data and the size of the LLMs increase, we see that the performance of these LLMs actually are pretty good. So yeah, in my own opinion, if we just train LLMs in this paradigm, which I just let it to generate a sequence of plan, that basically means that the search process is actually hidden in some weights in the LLM. So that may be a limitation, right? And I actually remember that some researchers tried to have external, for example, tree structure to kind of guide the LLM to do planning. Yeah, that's the one way. Yeah.
Just a follow on from the last question. So Tokens are obviously very coarse-grained, and if the next token is the letter R, that's not particularly useful. Have you looked at large concept models in the past? They kind of flew under the radar a little bit, but they're a bit more coarse-grained and look at like sentence-level concepts.
Not really.
Okay, I have one question of my own. So, when you're talking a lot about fine-tuning and training all the models afterwards, but especially since you reduce the amount of examples that you have and context windows, especially of large models, keep growing, have you tried just putting all the examples along with a query and then see what the performance of this is instead of using the samples for fine-tuning?
I haven't tried that, but it's indeed a good exploration. Yeah, I think nowadays, for example, Gemini, they allow 1 million tokens as input. Yeah, that's pretty cool. So maybe, yeah.
Okay, let's thank the speaker again.